Okay. Okay, so welcome back. I just wanted to say that this story about changing the B, it's probably the first time I present it in a lecture. But I mean, it's written in papers. In fact, it is written in the paper of with Bertrand in 2007. But I very rarely have the occasion to go that far in presenting topological recursion, so that I can lecture on it. What I wrote here. So you see that changing the B corresponds to cutting the edges of a graph in all possible ways. And what you get in the end is a polynomial in kappa. Before going a little bit further, let me make a remark. So let's start again with our example of a genus 1 on the genus 1 curve. Let me observe something. So here, the omega I choose, so my omega was dz1. My omega of z was just dz. Okay, and dz is a form that is holomorphic on the whole torus. It has no pole. Okay, it's a well-defined form. It's holomorphic everywhere. It's a holomorphic form. In fact, on the torus of genus 1, there is a unique such form up to a scalar factor. Okay, I mean, in genus G, the dimension of the holomorphic forms is G. And in genus 1, it's 1, so there is only 1 up to multiplication holomorphic form. And just let me observe the following thing. So I told you that if we choose G2, then the integral of B along the A cycle is vanishing. But the integral of B along the B cycle is not vanishing. But what does it give? Let's compute the integral of B. So let's take Z2 belongs to B of B of Z1Z. So sorry, well, let me call it Z, ZZ2. So we integrate Z2 on the B cycle. You can compute it. And it will be a one form in the variable Z. It will be a one form in Z. Just observe one thing. For every value of Z, this integral can be computed and it will have a finite value. Imagine that you take Z exactly on the trajectory of the B cycle. In fact, you could shift the B cycle a little bit to the left or to the right to compute it. I mean, since this is meromorphic, this is invariant by homotopic deformation of the integration contour. So you could always deplace your contour a little bit. And if you go to the left or to the right, there could be a difference if there was a residue. If there was a simple pole, I mean, since B has a pole, if it had a residue, it would make a difference. But B has no residue. The Weierstrass function has no residue. There is no residue, so basically you get the same value whether you compute it from the right or from the left. Just to say that the result of this is a one form in the variable Z that will be holomorphic everywhere. So it has to be proportional to dz. And in fact, if you compute it, it is 2 pi I dz with this B. Okay, so it is 2 pi our omega. So in general, let us assume that we have chosen an omega. So in general, when I will do my change of B, let me assume, so as I told you, I could take, so let us assume that there exists some, let's call it gamma, such that omega is the integral of gamma of B in one of the two variables, and then it's one form in the other variable. That covers a very large number of cases, and later I will introduce also a notion of generalized cycles. And in fact, well, basically a cycle is something that acts linearly on B. It's like a one form acting on the space of forms. I mean, it's an element of a dual of forms. And when you apply it on B, you get a one form. So, I mean, it does not have to be really a true cycle integral. It can be anything. And basically, what I just want to say is that, in fact, every omega can be represented in this way. In fact, it's not a special case. It is the general case. But here, let us take the case that I was discussing here, where we want where the omega is an integral of the B on the B cycle. So here in our example, gamma was the B cycle. Okay. Just to say that in my graphical representation, this omega was an integral over some gamma of the B. On one of the two ends is integrated on gamma, on the other end is the one that will be there. Okay. So somehow Z is there, and here this variable you integrate it on gamma. Just to say that the blue dot represents the integral. So graphically, every time you have a blue dot, it means that you take the B and integrate it on gamma. And similarly, this thing here that I draw here, it will be, so it depends on variable Z on sigma A of Z. It is, by definition, it will be the integral for Z1 belongs to gamma of K of Z1 Z. Again, the blue dot means integral over gamma. Okay. So just the idea to retain is that blue equals blue on something. So now let me give the final. So basically, what that means is that K means omega 1, 1 plus integral over K over gamma of B. That's this guy. Times kappa times integral over gamma of omega 1, 1, because we recognize omega 1, 1. Plus, okay, here we recognize an omega 0, 3. And the two ends are integrated over gamma. Well, let me say this was the Z1, and here we have the Z1 on the integration variable. Here we have Z1 on the two variables that get integrated on gamma, plus, and here we have, so this one is an integral over gamma of B of Z1 dot times kappa times now integral over gamma of omega 0, 3. There is an over kappa, kappa square. Okay. We could also compute d over d kappa of omega 1, 1 and evaluate it at kappa equals 0, but we'll get rid of the last term. And we see that this is integral over gamma of omega 0, 2 of Z1 dot times integral over gamma of omega 1, 1 plus integral over gamma of omega 0, 3 of Z1. Okay. Just another way of interpreting that. And then the general theorem is the following. D over d kappa of omega gn of Z1 Zn equals integral over gamma omega g minus 1 n plus 2 of these are the two variables that are integrated, plus sum over G1 plus G2 equals G, and I1, I2 equals Z1, Zn, omega G1, 1 plus I1, the first variable I1, omega G2, 1 plus I2, the second variable I2. In the end, this is quite simple. And evaluated at kappa equals 0. If you want to compute higher derivatives, the second derivative and so on, you just recursively apply this formula. And it turns out that this formula is so you see that d over d kappa is like a quadratic operator acting on your forms. And this can be related to the BCOV formalism. This can be also related to the R matrix formalism in Giventhal formalism. And this is a very deep equation. This is also very closely related to the Hitchin equation, the so-called heat equation. It is a very, very powerful equation, and it's related to, it can be reinterpreted into BCOV, which is also called holomorphic anomaly equation. Holomorphic anomaly. This is related to a Het equation, to Hitchin connection, and so on. And it is the formula that allows to change the cycle on which you normalize your B. Well, I just wanted to present it. Another thing is that since d over d kappa is a quadratic operator, when you want to apply the formula several times, somehow you have to exponentiate this quadratic operator. And the exponentiation of a quadratic operator can be done by writing some Gaussian integrals. Well, exponential of a quadratic operator is typically what Gaussian integrals do. There is a way to rewrite the full summation now of all the powers of kappa with some Gaussian integrals, and that's extremely powerful. Okay, I will stop with this for the moment, just to know that this equation exists, and it's a very, very strong equation. Now let me come back to matrix models. Okay. And in matrix models, there are 2 points I want to discuss. One is what happens when you take deformations. What happens when you take deformations? I think this is chapter 5. Someone followed. Matrix models. Well, sorry, deformations. And the next chapter will be about integrability. So one in matrix models. Remember that I define Z to be the integral over, 1 over n factorial, integral over some, let's say, gamma to the n, or some gamma, d lambda, Vandermonde of lambda to the square, exponential minus 1 over h bar, sum of tk over k, twice of lambda to the k. K equals 1 to some, let's say, maximum d. D plus 1, maybe I called it. I call D the degree of D prime, yes. So it's D plus 1. Yes. First, I already made the remark that D over dtk minus h bar k d over dtk of log z was the expectation value of, well, basically acting with d over dtk will put down a trace of lambda k divided by k divided by h bar, but I multiply by k on h bar, so it just gives the expectation value of trace of lambda k. And another remark is that trace of lambda k, so remember that what I called W1 of x was expectation value. So the resultant was the expectation value of x minus lambda, which was also the sum over k of 1 over x to the k plus 1 expectation value of trace of lambda k. Okay? So you see that trace of lambda k is the coefficient of 1 over x to the k plus 1 in this formula. And I already said it. Trace of lambda k, expectation value, is residue at infinity of x to the k w1 of x. And minus, because residues at infinity have a minus sign. So in the end, this is minus residue at infinity of x to the k w1 of x. I will repeat this. Now I will take second derivative and so on. Okay. In fact, let me just say that when you act with, so instead of acting on log z, now let me react on W1. W1, it's an expectation value, normalized, so it contains the denominator 1 over z. Well, okay, let me do the calculation in detail. Let's act again. Let's act again on minus h bar, let's call it k prime d over dt k prime, w1 of x. Sorry, I don't need k prime. Okay. So this is minus h bar k d over dt k of 1 over z times integral of gamma d lambda, 1 n factorial, d lambda delta of lambda square. So here we have a trace of 1 over x minus lambda, exponential minus 1 over h bar, sum of tk over k, trace of lambda k. Or let me call it tj over j, trace of lambda j, sum over j, because k is fixed. Okay. When I act with d over dtk, I act here, and this brings down a trace of lambda k, and I also act on z, which depends on tk. Okay? When I act on z, I already know what is the derivative of z, and it will be, it will give such a thing. So let's start with the term where I act here. So I will get 1 over z times n factorial times, well, so I will get another trace of, so, well, basically it's easy to see that you will get an expectation value of trace of 1 over x minus lambda times trace of lambda k. And then there is the other term plus the term where you act on z. Okay, I'll let you do the computation, but it will give a minus expectation value of trace of 1 over x minus lambda times expectation value of trace of lambda k. So basically it will be our cumulant. And again, this is minus the residue at infinity of dx prime over times, sorry, of x prime to the power k dx prime times expectation value of trace of 1 over x minus lambda, trace of 1 over x prime minus lambda, because taking this residue in the variable x prime will precisely extract the trace of lambda k. So this is minus residue at infinity of x prime to the k dx prime times, sorry, and this is the connected, the cumulant, and this is what I call W2 of x on x prime. So let me show you what is important in these two formulas. Here we take a derivative of log z with respect to one of the times, to respect to one of the parameters, and computing a derivative is the same thing as computing an integral of W1. Computing a derivative of W1 is the same thing as computing an integral of W2. So I don't know, this is related to the general philosophy of what people call spatial geometry. But the idea is that if you want to compute a derivative, it means that somehow you should compute the omega gns not for one spectral curve, but you need to compute them for a family of spectral curves. Whereas the integral is computed for a given spectral curve. You don't have to deform. I mean, integrals live on only one point, one spectral curve. Whereas derivatives with respect to the moduli, you need somehow to explore the full neighborhood, in your moduli space. Here, you just need to know one point in your moduli space. So this is a big advantage. You can relate deformations. So the general strategy is to relate tangent vectors of your moduli space to linear forms acting on your forms, Wn, at a given spectral curve. So this is the general strategy. So it may, in general, people think that derivatives could be simpler than integrals, but so somehow you exchange derivatives on the integrals. But in fact, it's very easy to compute. Well, first, these are not really integrals, these are residues, which is much simpler than integrals. You just have to extract one coefficient. But so, let me summarize what I just said. And then we shall translate that into the topological recursion language. So for matrix models, this property is true by construction. So let me summarize. So this is a theorem for matrix models. It's a very trivial one. I just made the proof. Is that d over dtk of omega gn of z1 zn, and be careful, you need to work that such that x of zi are fixed. So you work at fixed points. I mean, they're fixed points, I mean, in terms of where they are on the base curve. You take derivative at fixed points. This is important because the parameterization itself could depend on time, but everything should be parameterization invariant. So a way to fix the good choice of parameterization is to take the base as a good parameterization. And it's canonical. So it's always equal to 1 over k. Well, let me put an h bar. 1 over k residue at infinity of x to the k omega g n plus 1 of z1 zn, and the plus 1 is your integration variable. So this is just, so to go from there to there, you have to multiply by dx1, dx2, and so on. You see that the dx is there already. So that's a general property in matrix models. The deformations with respect to the moduli, to the coefficients of the potentials, are integrals of omega gn plus 1. In fact, it can be, well, so a particular case, a special case, so case gn equals 0, 1. So it's the case where h bar d over dt k of omega 0, 1 is 1 over k residue at infinity of xk omega 0, 2. So now to general situation for TR. So now consider not one spectral curve in TR, but a family of spectral curves. So let me call them family indexed by a time t. Let me call it ST. So it contains a surface, let me call it sigma t, and xt, yt, on the B index t. I mean, all of them may depend on time. All of them may depend on time, but let us assume, so imagine that there exists a linear operator, acting on forms. And let me call it gamma t. Okay. And such that when you apply such that for every t, you have that d over dt, h bar d over dt of omega 0, 1 is gamma t acting on bt, in the first variable. So the result is a variable in the other, so the result is the one form in the other variable. And so this was the case here. Here the gamma t, the gamma index tk, when it acts on on any form, let me say omega, is defined as 1 over k residue at infinity of xk times omega. This is what corresponds to that. So it acts linearly on omega. Let's call it a generalized cycle. Is every element of the dual of forms generalized cycles? The answer is no. First, the dual of forms is something huge. It's something very nasty. The dual of all possible forms is something really nasty. For example, it could be integrating forms together with a fractal measure. It would be something absolutely nasty. And then, in particular, when you would integrate the B, the first variable of the B, I mean, when you would contract the first variable of the B with your linear form, the result in the second variable would not always be a meromorphic one form. It could be something which is not analytic at all, which is even analytic nowhere. And basically, the definition of generalized cycles are precisely those, such that when you contract them with B, you get something meromorphic. But here, this is the case. This one is an example where you contract B with that, you get something holomorphic. Oh, sorry, meromorphic. Nothing, but in fact, it turns out that every tk was, in fact, the true parameters of this thing are TK over H bar. So it's just a rescaling. I put an H bar from the beginning. It plays no role, but somehow it's only TK over H bar that makes sense in this story. So that's why it's normal that it's D of, well, if you want, I could write it D of TK over H bar. Oh, sorry, here there is no, sorry. Oh, and that's right, there is no H bar somehow. Sorry. There is no H bar because I skipped a little bit detail. Here, this is the full W1 that you need to write as a sum over H bar to the 2G minus 2 plus N and so on. And when you identify the powers of H bar on both sides, you get this equation. And of course, since you identify the coefficient of power of H bar, there is no more H bar. So indeed, good remark. It was a mistake. Yes. So the idea is, if we consider a family, is there always a generalized cycle such that the deformation of omega 01 is the contraction of B with one of these generalized cycles? The answer is yes. It's not trivial to prove, but the answer is yes. But in fact, in most practical examples that you will be considering, it will be very easy to find it. But in fact, it always exists. But sometimes, I mean, and there are tricks to find it. Sometimes it's not so easy, but you will always find it in any family you are interested in. You will find it. Okay. Okay, so imagine that there exists such an operator, and in fact, you don't really have to imagine it exists. Then, but there you have to believe me somehow. But then the theorem. So theorem of deformations. Then for every G and N, you have that d over dt of omega g n is the gamma t contracted with omega g n plus 1, and this contraction is on the n plus 1 variable. So basically, if it holds for omega 01, it holds for all of them. Well, in fact, there are a few details to say. Okay, I'm skipping a few details, but somehow gamma t should have this support away from the ramification points. Or in fact, okay, I will not have time to do it in these lectures, but this space of generalized cycles is equipped with a symplectic form that you can call intersection. And one requirement for this theorem is that the gamma t has no intersection with cycles located at the ramification points. So basically, if in your family you move, you start to introduce, if your deformation introduces poles at the ramification points, you cannot apply this theorem. But as long as the poles that you introduce are, for example, here at infinity, you're fine. Okay. Okay, so and in fact, how do you prove this theorem? You prove it by recursion, of course. So you have to show, so you have to first study what happens to the derivative of k, and use the fact that k contains b and omega 01. Sorry, I skipped a detail. So such that this is true for omega 01 and d over dt of omega 02 is gamma t omega 03. So if it's true for both of them, then it is true for all of them. Sorry, I skipped a detail. The reason why I skipped it and I didn't mention it in the matrix models is that whenever B is the Barman kernel, this second property is automatic. The Barman kernel always satisfies that, and it's called Rausch theorem of deformation. I mean, Rausch studied the deformation of the Bergman kernels, and the deformation of the Bergman kernel always obeys this equation. This is Rausch theorem. But if B is not the Bergman kernel, then you have to be careful, and you should check if this relation holds or not. Sometimes it holds, sometimes it doesn't hold. You have to be careful. But if B is not the Bergman kernel, you could use what I just said before. Say that, so you have a way to deform to, so if B is the Bergman kernel plus some kappa term, then you can see what it gives. I mean, there is always a way to work with it. All right, so this means that there is a way to compute deformations of the omega GNs of spectral curves. So I showed you that I showed you in the two previous chapters how to deform. So in the previous chapter, I showed you how to deform B by adding this kappa term. Now I show you how to deform basically omega 01. And with these two tools, you can start from any spectral curve and deform it to another spectral curve. And by combining this, you will get a lot of interesting things, and in particular, this is how you make re-evening to a cohomological field series and things like that. I will not have time to do it now. My last part is I would like to talk now about integrable systems. And I think this is chapter 6, integrability. And I will come back to matrix models. Now, I already told you, let's define psi of x equals the expectation value of a characteristic polynomial. So I already told you about this. First of all, it is obvious that it is in matrix model, this is a polynomial of degree n. It is well known that, in fact, it's not only any polynomial. It's a polynomial that is in a family of orthogonal polynomials. So I don't know if you have heard about that, but I will talk about that later. But now let me just make the following observation. So it means that psi of x is 1 over z times integral 1 over n factorial, integral over gamma to the n, d lambda, lambda to the square, exponential minus 1 over h bar, sum of tk over k, trace of lambda to the k. And so here I should multiply by determinant of x minus lambda. I don't know if you know the following formula, which is very useful. This is also the trace of log of x minus lambda. To see it, just write that this is a product, and this is exponential of a sum of, well, I mean, this is a trivial formula, but it's very powerful. Because let's write it as exponential of trace of log of x times 1 minus 1 over x lambda. Which will be exponential of, so trace of log x is just n times log x. And exponential trace of log, and let's expand at large x, let us expand the log. So it will be minus sum over k equals 1 to infinity, 1 over xk times xk. Sorry, what am I? Yes, 1 over xk indeed, trace of lambda to k. So here, coming back to the thing I had here, I have exponential minus sum over k equals 1 to infinity, 1 over k, xk, trace of lambda to a k. Okay, I'm doing it heuristically, or this can be made rigorous. But I'm just working at the moment heuristically, but just observe that this term looks very much like this term. Here the sum was from k equals 1 to d plus 1. And here we have the sum with 1 to infinity. But in the end, so I'm going to re-raise that. Oh, sorry, and I forgot the x to the n. So exponential. So let me put an x to the n here in front. So, well, let's put these two terms together, and you see that somehow it corresponds to having changing tk to tk plus h bar 1 over x to the k. For every k. In fact, let me introduce the vector t, which is the vector of all times, t1, t2, t3, and so on. It's, but it stops td plus 1, and then it stops 0, 0. Okay. And let me introduce another vector that I will call x, which is the vector 1 over x, 1 over x squared, 1 over x cubed. Okay. This is called as Sato's notation. So basically, we have just, so this formula just means that we have changed t to t plus h bar x. Or in fact, since, as I said from the beginning, all depends only on 1 over h bar times t, 1 over h bar times t was changed to 1 over h bar times t plus x. So the true times, which are 1 over h bar t, are just changed by x with a coefficient 1. So in the end, let me recall z, my z. Let me call it z of t. And what do we get here? We get that this is recognize that this full integral here. Okay. In fact, let me introduce as well a t0. I should have introduced in z. I should have introduced a t0. So let me call it minus t0 minus h bar 1 over h bar t0. And let me start at t0. And the t0 will be log x. So then I don't have to. So this term is now included in the exponential minus, no, plus. So n, so 1 over h bar log x. And sorry, there is a minus sign here. So now this is correct for all times starting from 0. And you recognize that this expression is just, so in the end, what do we have? We have that psi of x is z of t plus h bar x over z of t. in fact, let me write it z of h bar minus 1t, and then it's z of h bar minus 1t plus x over z of h bar minus 1t. And this is Sato's formula. Very famous in integrable systems. Sato's formula says that the wave function, which will be called the Baker-Axler function in integrable system, is the shifted partition function divided by the partition function. Or in other words, a wave function can just be thought as a partition function, but with shifted times. Now let's see what it will become when we do the small h bar expansion. So we shall use topological expansion. Small h bar expansion. So now, okay. So let me start over with the following observation. So z times psi of x was integral 1 over n factorial, integral over d lambda, delta of lambda to the square, exponential minus 1 over h bar trace of v of lambda, and times, again, exponential trace of log of x minus lambda. Now let's use something very subtle, that is the log is the integral of 1 over x minus lambda. So 1 over n integral d lambda, delta of lambda to the square, exponential minus 1 over h bar trace of v lambda. Let me call it d lambda. That will shorten everything. D lambda, so it's our measure, times exponential. And let's write this as integral dx prime, 1 over x prime minus lambda, let's put trace, up to x. Well, we would like what would be the starting point of integration.
Sorry to interrupt. Can you say again the role of this little d, the d there?
The small d, this d, it was the degree of the potential, if the potential was polynomial. Let me say something. We are here, this Sato's notation amounts to trying to express a log in the basis of polynomials. So you are trying to put a log in the C of x. That does not really work because log is not a polynomial. So log is not in C of x. That's why you need an infinite number of times. Somehow there is something not so well defined here. There is something not so well defined, but the integral we started with is perfectly well defined. The notation has some, okay. I mean, as long as you work formally with series and all that, it's fine. But it's not really well defined, this infinite number of times. So basically the log.
It's just a fixed integer that you.
Yeah. Yes. So d was a fixed integer. It's the degree of your potential you started with. For example, if you started with a Gaussian matrix model, d equals 1. If you started with quartic, d equals 3. Okay. So here I would like to integrate from infinity, but you cannot really. So let me introduce this regularization plus n plus 1. Okay. Let me rewrite it this way. Okay. Well, in fact, I will often be tempted to say that, well, in fact, what interests me in this thing is only the lambda dependence. So basically, this is a kind of independent of lambda, independent of lambda. And to simplify, let me recall all this integral from infinity to x, regularized. Let me put this quotation mark, dx prime over x prime minus lambda. Okay, meaning that to really compute this integral, you need to subtract the pole at infinity and re-add it outside. But it will be shorter to write this. Or let me write reg. Okay, let's continue. Well, let me put the n factorial on the left. Integral d lambda. And let's expand the exponential sum over n, 1 over n factorial, trace of, and trace of, integral infinity to x reg, trace of dx prime over x prime minus lambda to the n. I'm going to put it to the power n, but instead of writing it to the power n, let me write it in this way. Okay, I've just done the same thing. Well, which is integral over d lambda, sum over n, 1 over n factorial. Let me write it in this way, integral over x reg d, and you see you have this product of traces. And when you compute the integral over the product of traces, the integral over product of, let me write it this way. And this quantity is precisely the expectation value of a product of resolvents. And it's precisely what I called Wn hat, because I don't take the cumulant yet. And times dx prime 1, dx prime n. So this will be our, in fact, omega n's. And this is not yet normalized, but well, this is multiplied by n factorial z. So in the end, what do we have? We have that psi of x equals sum over n, 1 over n factorial, integral infinity x reg of w hat n of x prime 1, x prime n, dx prime 1, dx prime n. Fine. Now you want to re-expand Now, remember that W hat n was Wn plus the sum of our partitions mu. Well, I mean, it was a sum of our partitions of all the variables, x prime 1, x prime n, of the product over I equals 1 to the number of parts of W, now the cumulant of mu I of mu I. Basically, I re-express everything in terms of cumulants. Now it's a combinatorial exercise, so you see that you have factors, and you will realize that in the end, you can, so you have products of such integral involving the cumulants, and you can resum the series. It's an, you should do it as an exercise, but this is just a very famous combinatorial method. Well, I mean, the idea is that the generating series of cumulants is the log of generating series of non-cumulants, and basically, or said another way, the generating series of the hats will be the exponential of the generating series of cumulants. So in the end, what do you find? You find that W psi of x equals, in fact, the exponential of sum over n, 1 over n factorial, integral of Wn, but now without hats. And this is more or less the final formula. And it's, all of them are regularized. In fact, the regularization is important only for W1, for the cumulants. Only W1 has, is not integrable at infinity. W2, W3, and so on are all integrable at infinity, so they don't need regularizations. So in fact, I could also rewrite that as integral exponential sum over, so let me put the n equals 1 first, integral of to infinity of W1 of x prime minus 1 over x prime dx prime plus n log x, okay, times exponential sum n larger than 2 of 1 over n factorial, and now you need, all of them are really integrable. No, sorry, I'm cheating you a little bit. No, that's correct, sorry. Okay. Okay, so that's it. So the others are really honest integrals. So this is so it just says that the wave function can be re-expressed in terms of the Wn's. And the Wn's, now let us choose, so now let's do the h bar expansion. Wn times dx1 dxn, so which is what I call omega gn, is sum over, is omega n, is sum over g of h bar to the 2g minus 2 plus n omega gn. So let's put that in the psi of x equals exponential. And again, we need to do something special for, so if you want, using this formula, sum over g and sum over n, h bar to the 2g minus 2 plus n over n factorial, integral regularized of omega gn of, well, I mean, just the n variable here are the ones you integrate. In fact, that's not totally true, because for omega 02, you remember I defined, so omega W02 dx1 dx2 was not my omega 02. It's I added dx1 dx2 over x1 minus x2 to the square. So omega 02 is not the W02. So if I take that into account, I should do something special for gn equals 02. But somehow this is what the reg means here, is that I take into account also properly the 02, and I take it by this formula. So let me rewrite in another word what that means after taking into account the regularization. I have something to do, special to do only for omega 01 and omega 02. let's write the omega 0, 1. And the omega 0, 1, as I said, is so n log x plus integral from infinity to x of omega 0, 1. Sorry, and there is, so n is the same thing as h bar inverse plus omega 0, 1 minus of, let's call it, of z prime minus, or well, let's call it x prime, dx prime over x prime. Okay. So which is regularization. For the omega 0, 2, I let you compute with this formula, and in the case of a genus 0 curve, what you would get would be, sorry. Okay. So here you have to compute in 1/2 of integral from infinity to x, integral of infinity to x, omega 0, 2 minus dx1 dx2 over x1 minus x2 to the square. Okay, and then exponential sum over g and n, such that 2g minus 2 plus n is strictly positive of h bar to 2g minus 2 plus n over n factorial, integral now infinity to x omega gn. So this is the formula that you have seen probably in many places. Okay, so this formula holds for matrix models. And it defines the wave function, the Becker-Accuser function for matrix models. And as I said, this Becker-Accuser function in matrix models, it's a polynomial, and it's an orthogonal polynomial. It satisfies plenty of beautiful properties. And in particular, it satisfies determinantal formula, Fay identities, Hirota equations. I mean, it satisfies plenty of relations. And question, can we define some similar object in general topological recursion? And basically, we shall take this equation as a defining property, and then we have to show that if it satisfies some Hirota or something like that, or quantum curves. And for people who work on, I don't know, non-abelian Hodge correspondence, this is supposed to be the, this should give a section of a flat connection. Well, let me generalize a little bit. Let me generalization. Let me compute the expectation value of product of determinant of xi minus lambda to some power alpha I. Sorry, let me. How much time left? Okay. Let's take this expectation value, and to simplify, let me assume that sum of alpha I equals 0. If I take this assumption, there will be no regularization needed. You can redo the same thing I was doing. This is the expectation value of product over I equals 1 to k of exponential alpha I trace log of xi minus lambda. And you redo everything which I did, and what you find is that this is exponential of sum over n of g on n, h bar to 2g minus 2 plus n over n factorial. And here I will do sum over, so integral. So let me introduce this notation, what I will call sum over. Okay, let me define sum over I equals 1 to k of integral alpha I times integral from infinity to xi. It is a linear operator that acts on forms. And let me call it integral over gamma. That's a definition. So this is the final formula that works for matrix models. Okay. Where did I want to arrive with this? You may wonder. Okay. So you see that so this formula, you can prove it with matrix models by just using the fact that the determinant is exponential trace log. The log is an integral of one of a resolvent, and you play with the cumulants and you arrive to this formula. So this is a formula for matrix models. This is a consequence of a definition. But you see that but in the right-hand side, there only appears the omega gns, and you don't have to, I mean, you could take this formula for omega gns coming from an arbitrary spectral curve. It does not have to be related to matrix models. Now, why would these functions be interesting? Why would such functions be interesting? So, and I gave a name to that. I called them psi of. So remember, I used the divisor notation plus alpha 2 dot x2 plus alpha k dot xk. And so this can be, so now let me take a, definition in TR in general. And so let's call that the wave functions. For a divisor. No, they don't have to be integers. But then I will state a theorem that will be valid only if they are integers. Oh, not a theorem, but a conjecture, in fact. A divisor sum of alpha I xi with degree 0 with sum of alpha I equals 0. I mean, if sum of alpha is not 0, you just have to regularize. If sum of alpha is 0, then you don't need regularizations. So it is, by definition, it is exponential sum over g and n of h bar to the 2g minus 2 plus n over n factorial, sum over, and let me call my divisor d, and this thing, let me call it the integral on the divisor d. So this guy now can be defined on, in fact, I should really say points on the spectral curve. In the matrix model, I was a little bit sloppy with whether we should choose the first sheet or second sheet, I mean, signs of the square root, but using the variables in the spectral curve, there is no ambiguity. Which means that you don't get the same value if you take the zi's in the first sheet or in the second sheet. So you get two different psi's. So this is just a definition. Why is this definition useful in any way? That's where I want to arrive now. In matrix models, these functions, as I said, satisfy many beautiful properties. And let me state one of the properties. Let me say that in matrix models, so in a random matrix theory, that means, so the psi of 1 times x1 plus minus 1 x2 is the expectation value of determinant of x1 minus m determinant of x2 minus lambda. Okay, and I multiply it by the x1, the x2. By x1 minus x2. Which is in fact the regularization of my omega 02 I talked about. And very often this is called k of x1, x2. Of x2, x1. It's not the same as the recursion kernel. Let me use a curly k. And it's the integrable kernel. And there is a theorem in matrix integrals. That is called the determinantal formula. But it should really be called the phi identities. I think it was some early version of this theorem were stated already by Mehta Godin. I think in the 60s already, and then, and plus, in fact, I think the first true proof came from Berger in the early 2000s for the general case. But the theorem is the following. It's that psi of x1 with coefficient 1 plus x2 plus xk minus x prime 1 minus x prime 2 minus x prime k. So it means that you have k points with weight plus 1 and k points with k minus 1. So it's a divisor with 2 k points, and k of them have plus 1 and k of them have minus 1. And it is equal to the determinant over I and j between 1 and k of psi of xi minus x prime j. It's as simple as that. In other words, a 2k point function is a determinant of 2-point functions. In integrable systems in general, I mean, the way physics presents integrable systems, usually they say that the, that the scattering of particles is entirely characterized by scattering of 2 particles. So somehow the 2-point function determines every others. So this is true for matrix models. It's not so easy to prove, and this is why it was not done really early in the literature. It's not that trivial. It's kind of complicated. It uses basically the orthogonality relationship of orthogonal polynomials. It can be proved to be equivalent to Hirota equations, to precursor relations, to many famous formulas in the integrable system, and it's not at all trivial to prove. It's far from trivial. I mean, you can try to prove it just from the definition of a matrix integrals, and you will see that you will have a hard time. But the question is, could this hold for general spectral curves that don't come from matrix models? Can this be true in general for arbitrary spectral curves if you define the psi in this way? So the question, is it true that psi of z1 plus zk minus z prime 1 minus z prime k equals determinant of psi of zi minus z prime j? In fact, the answer, to be honest, is no. But it's true in many cases, and in particular, typically the cases of genus 0. It's not true in higher genus in general. But the thing is that there is a way to make it true. And it is to, well, somehow the reason why it's not true in general is that here we have taken a formal series of H bar. So it's just what people call perturbative. We have taken only into account the perturbative part of something. But to make this true, we need also non-perturbative terms. When you start, so there is a way to complete topological recursion formalism, and in particular to complete this formula with some extra terms that are non-perturbative, that have no 1 over H bar, that have no H bar expansion. There is a way to complete this formula such that it would be true. However, this is still a conjecture. This is not proved in most cases. However, if you take your favorite spectral curve and you compute the two sides, expand to order H bar 1, H bar 2, H bar 3, and so on, H bar 4, and so on, you will see that it matches. So if you start with a genus 0 spectral curve, typically you can, then there is no non-perturbative term, you can compute both sides and you will see that it works. And I was proposing to do basically the exercise for the airy, for the simplest curve, maybe this afternoon. So it is in fact, so the answer is, well, nearly. What I mean is that it's no if we don't take non-perturbative terms. And it would be yes, but with a question mark, if we take also the non-perturbative completion. The non-perturbative completion, in fact, instead of formal series, you need what is called trans series. I think that Paolo will talk about that in his lectures, trans series. And basically, trans series is that typically you would need to add inside the exponential some terms like exponential 1 minus 1 over H bar. So these terms have no H bar expansion. At H bar small, they have no such H bar expansion. So it's inside the exponential. So if you take into account such terms, somehow they are not visible in the asymptotic expansion, but they are necessary to make this equation hold. Yes. So, but as I said, this is not proved in general. This is a conjecture which has not been proved in general. It can be checked in many cases. It has been proved case by case for some cases, but it's still an open problem. However, I have no doubt that this is true. And you're welcome to try to prove it. It's supposed to be a hard conjecture. So in the matrix model, the way it was proved, as I said, the proof in matrix model is definitely non-trivial. It uses orthogonality relations, and it took a long time to rewrite a complete proof. Okay, it's not trivial. That's what I can say. How much time is left? Okay. In fact, I'm a little bit in advance on what I wanted to say. Let me start the example. Yeah.
In more general cases, is there an analog of this orthogonality relation?
Yes, it's the Hirota relation, but in fact, to be, okay, in the, I think the 80s, people like Miwa, Jimbo, Hirota, Sato, I mean, all the Japanese school of integrable systems developed a full formalism of these tau functions and all that, and they proved some equivalences between Fay identities, Hirota equations, Plucker relations, and all that. There is a whole corpus of relationships that have been developed in integrable systems. And in fact, the orthogonality is, so the orthogonality of orthogonal polynomials is a bilinear relation. And it is, so the orthogonality, okay. How can I say that? So if you define psi n of x, so let me talk about orthogonality. So the answer, well, just the short answer to your question is, should we use, I mean, what is more fundamental? Is it the orthogonality or the phi identities? In fact, what is more fundamental is the phi identities. It's easier to derive orthogonality from phi identities than the converse. And what is true more generally is the phi identities. The orthogonality relations depend a little bit on the details of your model and your spectral curve. And it's not so universal of how to write them, whereas phi identities are totally universal. So, I mean, the way you write orthogonality, and in particular to write orthogonality, you need to have some contour of integration on the measure and all that, and that would strongly depend on the details of a spectral curve. It cannot be written in a totally, in a so obvious universal way, whereas these ones are more universal. So, let me insist on putting the n here. So it is 1 over n factorial. Integral over d lambda 1, let me put really the d lambda n, product of I smaller than j of lambda I minus lambda j to the square, and product of exponential minus h bar minus 1 v of lambda I. To n, sorry, this is the z, and to make the psi, you still need to multiply the product from I equals 1 to n of x minus lambda I. And you need to divide by z, 1 over zn. The orthogonality relationship, and I think it goes back to Dyson on meta. In the 60s, I think, is that the integral of psi n of x, psi n over n prime of x, e to the minus h bar minus 1 v of x dx. Well, let's say it's on gamma to the n here, on gamma, is proportional to delta nm. And there is a proportionality constant that I think they call hn. Sorry, hn delta n n prime. In fact, it's not that difficult to prove. You have to use the fact that it's really the van der Waals and write it as a determinant and play with formulas about determinants, and you will observe that you get a determinant where some columns are not independent. And this gives 0 if n different from n prime. So this one is not that difficult to prove, and it was proved by the Dyson meta and all that. Okay, and from there, you can derive this relationship. But there is some work to do. Okay. So this was, so vice versa. Starting from an arbitrary spectral curve, so to answer your question, starting from an arbitrary spectral curve, we have this conjecture that it will obey some phi identities. Can we from there derive orthogonality relations or some bilinear relation? In fact, we can. And the idea is just, in fact, you can deduce these relations, these orthogonality relations in matrix models by taking some of the zi's very close to infinity and start doing an expansion, a Taylor expansion at infinity, and the Taylor expansion at infinity will imply these relations. This is the general method developed by Hirota, in fact. And there is a way to deduce these formulas from this one by taking, so basically you are taking limits of this formula where some points tend to infinity and you will get that one. And why does infinity play a special role? The infinity plays a role because that's where V has poles, and the gammas were chosen as paths that go to infinity in a way or in a direction where exponential V decreases and so on. And if you start from an arbitrary over spectral curves, you have to see where all the poles are, what are the paths that go to the poles, and so on. And you could formulate a kind of generalization of integrability, but it would depend on how many poles, what are their degrees, how you go to them, and so on. Okay. Okay. Right. Okay. So this was just this is more or less the end of my lecture, and I want now to enter a more specific computation on some example, which will be continued in the exercise session. But just so, so I've just somehow in this lecture so far, what I've done is kind of introductory lecture of how topological recursion arises in random matrices, arise from random matrices, and some of its properties. So how topological recursion was related to the spatial geometry, so this property that deformations are integrals, how topological recursion is related to integral systems, and this is this open conjecture. But so we see why it is true in matrix models, and the question is it true for more general spectral curves? And the answer should be yes. Or I also showed you the holomorphic anomaly equation, how they appear in matrix models. It's just by changing the B. So I gave you a hint of many other things that we have in the world of topological recursion. I didn't talk at all, or almost at all, about the link to algebraic geometry, Gromov-Witten invariants, cohomological field series, and all that, intersection numbers. I vaguely mentioned intersection numbers at some point, but I didn't talk at all about that. The lecture last year was much more oriented towards that. And there are plenty of other lectures about that. And I don't know if some people are going to lecture more about that in this section. Some people will introduce cohomological field theory, but not really the topological recursion part, Nitin, basically. And the link is very strong. But okay. So this was more an introductory lecture, and to give you a hint. And also, the one thing to retain is that random matrices is a very good kind of toy, playground to test ideas that would be true in general for topological recursion, for integral systems, and all that. So random matrices is just a very good playground where you have almost everything under control. So now let me go to my example. So I wanted to give some examples of spectral curves. Yes. So now let's do some examples. I will start with this curve, x equals z squared, and y equals z minus 1/2 of sum of ck z to the k plus 2. And b of z1, z2 is dz1, dz2 over z1 minus z2 to the square. And the sum over k could be finite. K equals, let's go from 1 to d. So first, in this example, let me compute dx. dx is 2z dz. It vanishes at only one point, which is the ramification point, at z equals 0, which I will call a. The involution sigma a of z is 1 over z. Is minus z. There is a first remark that you can make. So y dx is 2z squared dz minus sum from k equals 1 to d. Sorry. K plus 2zk. Tk plus 2 z k plus 1 dz. In fact, let me relabel the k, and let me start from 3 to d plus 2, k zk minus 1 dz. So first remark is that in the formula, we shall always need to evaluate y. So you remember the kernel, the recursion kernel, it involves y dx, so omega 0, 1 at z, minus omega 0, 1 at the involution, so the difference. Basically, it involves only the odd part of y dx, which means that all the even times will play no role. You can forget about the even times. They play absolutely no role. So you can put them or not put them, but will make no difference when you start computing y dx of z minus y dx of minus z. They will disappear. Yes, and so let's compute the recursion kernel. Yeah. Let's compute the recursion kernel. So k of z, 1z, is 1/2 of integral from minus z to z of dz1 dz prime over z1 minus z prime to the square over, so y dx evaluated at z minus y dx evaluated at minus z. So here you will see that you have dz minus dz, so that doubles. So you will get 4z squared dz minus 2 sum from k. So we need to take only the odd times. So 2k plus 1 z2k dz. And k starts from 1 to 1. Let me write k larger than 1. Okay. Well, you may wonder why I choose to put minus 1/2. I will show you why in a moment. It will be related to a special geometry. I mean, basically, this is the good notion of time. If you normalize, if you recall t as minus 2 times tk, you would have somehow the wrong non-canonical normalization. This one is the canonical one. So, yes, so let's compute 1/2, and the numerator can be computed. It is dz1 times 2z over z1 square minus z square divided by, let me put the 4 in front, so that's an 8. And let me put the dz there. So we have z square minus 1/2 sum over t2k plus 1 z2k. Let me in fact factor z square. So 1 minus 2k minus 2z square. So which is 1 over, so we have a 2, so we have 1 over 4 dz1 over z1 square minus z square times 1 over 1 minus 1/2 sum of t, sum over k, t2k plus 3 z2k, k now larger than 0, times 1 over z dz. This way of writing is very well adapted to taking residue at z equals 0. Basically, I started to write the Taylor expansion at z equals 0 here. So it's better to write it in this way. And you see again that there is a simple pole at z equals 0. And most of the exercises will consist in computing some omega GNs. Let me start by computing omega 03. Z1, Z2, Z3. So the recursion formula says that it is the residue that goes to 0, k of Z1Z. And here inside the bracket, we have b of z, Z2, b of minus z, Z3, plus b of z, Z3, b of minus z, Z2. In fact, both terms will give the same value. In fact, I could remove this one and put a 2 in front. We'll get the same thing, but you have to make sure. Again, just observe that the right-hand side, it's not clear at all that it will be symmetric in Z1, Z2, and Z3. It's not obvious. Let's compute it to convince ourselves that indeed it is symmetric. So first of all, in the right-hand side, nothing has poles at z equals 0. The B is perfectly holomorphic at z equals 0. The K has a simple pole at z equals 0. So in the end, the computation of the residue will just be somehow evaluating this at z equals 0. The evaluation at z equals 0. Let me write it in more details. That goes to 0. So 1 over 4 dz1 over z1 square minus z square over 1 minus sum minus 1/2 sum of t2k plus 3 z2k 1 over z dz, and here we have dz dz2 times, so let me put the minus dz dz2 dz3 over z minus z2 to the square z plus z3 to the square. And we have the other term, but this other term that I will not write, but is nearly the same. Let me remark that one dz simplifies. The other dz, make sure that this is a one form in dz, so we can indeed compute residue. There is the minus sign here. Let me put it in front. So there is minus 1 for the dz1. And the result of the residue is just evaluation at z equals 0. So, this gives a z1 square here when I evaluate at z equals 0. It gives a 1 minus 1/2 of t3. And this gives dz2 over z2 square, dz3 over z3 square. In fact, let me put this one also in front. Nice, it is symmetric. It is symmetric, so we are lucky. Well, as I told you, it will work in general. It will always be symmetric. So this is just this simple quantity. And it depends on the time t3. Now I want to illustrate what I talked about deformations. Let's compute the deformations with respect to some parameters, and in particular, let's talk about d over dt3. But let's talk about d over dtk in general. Before talking about d over dtk in general, let me, so now I want to talk about deformations and times. Let me make the following remark. Y dx, since dx is equal to 2z dz, y dx, in fact, I've already written it here. I want to expand, I would like to expand it into near the pole, near infinity. Yes, sorry. I want to expand it near infinity and, no, sorry. What am I saying? Yeah. I want to expand it near infinity. And near infinity, in fact, x, in fact, there is a ramification at infinity, and somehow x is not a good local variable near infinity. It is square root of x that is a good local variable at infinity. In fact, square root of x, okay. I mean, z equals square root of x. So, I mean, a local variable is something that will be well defined on the Riemann surface, and z as a function of x is not well defined near infinity. There is an ambiguity of choice of square root. So a good local variable would be square root of x at infinity. In fact, it's often good to take as local variable at near point. You always want to choose a variable that vanishes at this point. So a good local variable. And we shall use the local variable at infinity, which I will call xi, which be 1 over square root of x. Or in other words, x equals 1 over xi squared, which also means that dx is minus 2 over xi cubed dxi. And let me rewrite everything in this local variable. So y was so z, which is square root of x, so which is 1 over xi, minus 1/2 sum of t k plus 2. And so z was xi to the power minus k. So y dx is minus 2 over xi4 dxi did I make something? Yes. Plus sum over k, tk plus 2, psi minus k minus 3 d psi. Let me shift the indices minus k minus 1 d psi. Well, let me write it is sum over k of tk minus 2 delta k3 psi minus k minus 1 d psi. You see that tk minus 2 delta k3 is the residue minus residue at infinity. Sorry, I changed the sign. Minus. So then there is a plus residue at infinity of psi to the k y dx. This is why now I say that this is the good normalization somehow. If you want to define the times associated to a certain spectral curve that has a pole here at infinity, you should choose the canonical local variable at this point. And the times are the coefficient, are the Taylor coefficient at that point. These are the good times. These are the times with which we'll get KP hierarchy and all that. This is the kind of canonical normalization of your times. And now, and you see, this is one of these linear action on a one form. So this is something that. So how much time? Okay, so I will stop there. But so yeah. So the exercise will consist in now studying what happens when you compute d over dtk. And see that it holds in topological recursion. So, well, let's go to it now.
About this last point, so you think that someone gives you a spectral curve without signs, you have a canonical.
Yeah. 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 Yeah.
And you would keep x and change. I mean, he had x, and you just change y. From my perspective, it could be many ways. Is it?
So, sorry, I'm not sure what you mean here.
Oh.
So remember that the spectral curve comes with a projection. I mean, x is a projection to a base, and somehow it is fixed. You have a fixed projection to a base, and to define the canonical local variable, you need to define, in fact, from the variable on the base. Somehow, why do you want to use a canonical variable that is defined on the base? It's because then, when you want to compute derivatives, you want to make sure that your variable does not has no. I mean, is constant. You want to work with a constant parametrization. I'm not sure I understood your question. You can also deform X. And indeed, you see that here I start with T3. And usually in KDV and so all that, you also have a T1. And in fact, the T1, if you would extrapolate this formula for T1, so you would have to take k equals -1, and this would seem to correspond to a pole in Y. However, this is not the right way to do. In fact, T1 will more be something there. I know that, for example, Paul Norbury and others want to study what happens when you put a pole here. This happens in many interesting problems. So you could introduce a pole here, but it's not the T1 in the way I define it. It's another time, it corresponds to another type of singularity, and it's not the T1 in my definition here.
But if you were to shift x with the T1, why
Indeed, but when I want to take derivatives at fixed x, if I take a derivative with respect to T1 at fixed x, I will see it. Because, so somehow if I write x equals z squared plus T1, well, no, what you say is not totally true. So basically, it means that z equals square root of x minus T1, so which means that y is square root of x minus T1 minus 1/2 of sum of tk plus 2 x minus T1 to the power k over 2. So you see T1 everywhere, in fact. So when you start to compute derivative with respect to T1, it makes
even if omega gn don't depend on T1, it would just stay that. But once you change from
Yeah. Yeah. So if you want to use the canonical variable, then you see T1. I mean, it's just because z is not really z is just a dummy parameterization, and it has no meaning by itself. If you want to, I mean, the true, I mean, a parameterization that is more universal is really in terms of x. Maybe we go to lunch. Mm.
Then you assume that